Any question? Those who are there, you have a question? Well, if you don't have a question, we can generally talk about the course, right? In fact, yeah, right. So there's no question really. Fine. So basically, this course, it's intended as a postgraduate level course, uh, mainly meant for civil engineers, right? Or those who are working in the concrete science and technology. I don't call it concrete technology because concrete technology we are covering a little bit, not much. Technology is related to making concrete, right? Something like which we have talked about, ready-mix concrete. But some or other, um, the name has gone to concrete technology. Perhaps, uh, perhaps that it can be attributed to Adam Neville because it's his book, which was almost like a Bible for many many years, and it's a good book. Late Professor Adam Neville from UK. So he was the first one to compile a book on the subject. Now, what is technology? It's little bit since I have time, and they have been already going through NPTEL videos. So technology is science-based engineering. Question will come, what is engineering? Well, look at this. Engineering was there for more than 2000 years or even more. The day human being came out of the cave and made a portal and two such portals and put a cover to it and cover it up from all sides to be safe from wild animals and environment. That's engineering, sheer experience. Who invented? That's engineering. Because generalization was at that time was relatively missing of the nature's understanding of general understanding of the nature was relatively missing at that point of time. But about 400 years back, starting with Galileo Galilei, modern science, one can say, started, which means that we try to understand the nature and generalize the nature around us, physical nature around us, as we observe. And it is individual, not individual specific. You observe, Abhishek observes, Sandeep Saab observes. It will be all same. So elastic modulus don't change with person to person. Many other things which are subjective can change from person to person. So they are generalized and independent of person. And any part of the world, they'll be same. So there are laws of nature created. Therefore, this is science. And science-based engineering, that means you look from the nature's laws, that becomes technology. So if you look at concrete, it is still largely empirical, based on simple observations. Understanding of science has started coming. I point it out. I mean, I think it is, in my opinion, it's about 100 years, starting with Duff Abraham, generalizing. No, not Muhammad Adam. Sorry. No, it is Adam Neville, not Muhammad Adam. No, not that. Not that. I think somebody said Muhammad Adam or something. No. That's Adam Neville. Concrete technology. Achha, your name is Muhammad Adam. Excellent. But the book is by Adam Neville, Concrete Technology. It's almost like a Bible. And it's another thinner version along with Professor Neville, which is disciple, his student, Brooks, worked on Crip. Neville and Brooks. That's easy to read a book. So Neville is very well known book, right? And that's incidentally matches with your name, A.M. Neville. Yes. So A.M. Neville. All right. Um, I think he did come from East Europe, if I'm not wrong. Maybe from East Europe originally. Anyway, but he was a British citizen, vice chancellor of University of Dundee, where Professor Dean, another famous man in the area of concrete science and technology. So coming back to my course again. So science started looking at generalizing. So strength is a function of water cement ratio. That's the first generalization one would say, although things like weaker separators were there earlier, right? So this is the course, and say postgraduate level course. In undergraduate level course at IIT Delhi, or I'm sure at many other places now. I mean, they were not there earlier, but now they're there. In my time, they were not there actually. But ITD and ITM, they were, I'd say that they were quite pioneer in that respect. My professor, Professor Krishnamurthy, started at IIT Delhi, this particular course, and concrete, this deals with uh, behavior of concrete, understanding of concrete as a particulate material system packed together and then bonded with some sort of cementing material. That's what it is today, right? So in the bond between those particulate system is some sort of bonding material, which initially should be, by and large, should be in plastic state. That means there should be, solid plus water, making it a kind of plastic, right? Water, I mean, liquid is usually, uh, it's a fluid and which uh, follows Newton's law. No, Newton's law of viscosity. Basically, shear stress is proportional to uh, uh, strain rate, and the constant of proportionality is actually viscosity. You would have studied in fluid mechanics. Shear stress is proportional to velocity gradient in a pipe. It's the same thing written in a slightly different manner. So it should be plastic and under little stress. So once you give a stress, it should flow on its own, and that stress is called yield shear stress. So that's kind of scientific understanding that has started coming into concrete, although we didn't touch much upon it. So concrete is actually a material which initially is plastic, but then the reaction of the binding component with the liquid component of the binder system makes it solid, or sometime in concrete, of course, the reaction, that is cement reacts with water. That reaction, since all water is consumed, we call it hydration, right? Uh, in chemistry, hydration. Uh, there are other similar terminologies like hydrolysis, etc., etc. So this is hydration reaction, right? It gets hydrated, forms hydrates. And there can be other concrete like epoxy concrete where it is polymerization. But we didn't talk of that much here. So this, once it reacts, hydrates, it becomes solid. And occupies, the solid product of hydration occupies more volume than the original liquid water and the solid. I mean, original volume of the solid, right? So new solid is occupies more after taking water into reaction, and that's how solid concrete is formed. Now, this is an engineering materials used in engineering. Therefore, we got to look at its first making property. That's what we call, in a very scientific term, uh, one would be calling uh, rheological properties, right? And then in empirical way, we'll call them workability. So certain things. So initially, you got to look at that, how easily you can mold it. That was the first thing. Then once you have molded it, solidified it, does anything happens during solidification? It should give me sufficient time for its casting to be done. Uh, and mm, then finally it should become solid with definite size, shape, and volume. That's final setting. And then it must, since it still reacting. It's not instantaneous reaction. The process, it starts gaining strength, or what we understand by strength can force, withstand forces. Load, if you put force, civil engineering we call them load. So it should be able to withstand the load or forces. Normally, axially we test them. So therefore we look at strength properties. And in the meantime, we started looking into some of the production issues, which is more of the technology side of it, right? So one would call them now concrete science and technology, and this course has both. So technology is of production, which is again should be science based. So you have got ready mixed concrete, pumpability, pumping, vibration, and those things we talked about, and they were classically called as concrete technology, one would call them, right? So technology of making concrete. And then once we have looked into that part of it, right, we got to also look into other ingredients that comes into concrete. Together with that, and how do they modify this property? So these are admixtures. So one got to study the admixture which are there, and one of the common admixture which is very, common admixtures which is used is called uh, water reducing agent or plasticizer, super plasticizer, hyper plasticizer, very high range water reducing agent, high range water reducing agent, etc., etc. So they essentially try to minimize the consumption of water into the system for, making them moldable, and that is very commonly used. But there are other kind of property modifiers which we call them admixtures. But then there are modern kind of mineral materials uh, which are waste somewhere, right? Waste material. So like the fly ash coming from the coal, ground granulated blast furnace slag coming from uh, steel industry, then semiconductor industry, from semiconductor industry, silica and condensed silica fume. All these products which come from other industry, they find good use in um, as what you call additives in concrete, relatively small quantity additives in cement composite system, hydraulic cement composite system. So we study about them also in the course, and we do study the properties of the particulate system that should be bonded. That is your aggregation of material, we call them as aggregates, and there are different sizes we use. So some of them we call them fine aggregate, some others we call coarse aggregate, right, which are larger sizes. So that is what it is. That's part of the course, up to about 5-6 module. But then man-made materials have always the problem that they have a tendency to uh, come back to their natural state because you have produced them with the expense of energy. So since you have produced them with the expense of energy, they'll have a tendency to come back to their natural state by dissipating that energy. Now, this means that this material can degrade over a period of time. That means dissipating energy means through chemical reaction. So some chemical reaction, like that's what the thermodynamics tells us, that if you've given some energy, it will have to come back to their original state, right? So free energy is high, it will have a high tendency to react, right? And the product will have much less free energy compared to the reactants. So cement and surrounding material, their energy, if it is high, free energy which they can dissipate, is exothermic reaction. That is why reaction is water. So reaction is anything else, it can dissipate that energy, and therefore they have a tendency to degrade. The material has a tendency to degrade, which means the element, structural element, which has used concrete for its making, may deteriorate. And if it deteriorates, then you have to repair it, mend it, right? And that's related to what we call durability. It has to be durable, and quantification is durable. Durability is in terms of time up to which it will remain functional. It can be satisfactorily used, functional, and will not reach a serviceability limit as we define in limit states. So that's another section of the course. But then there are certain other types of concrete which have come of late. We have also discussed this. So in the meantime, if there is somebody else having another question, I can take it. I can take that question. If someone else is having another question, anybody else is having any question, right? So I can take that, right? So any question from anywhere. Otherwise, I'll also discuss the second part of the course. Go on talking. But if you have some questions, it's good to answer. If you have some question which I should be answering, I'd like to answer. I'd like to very much answer. So any question? Any question? Any question? Hmm. Any questions from anybody? Any question? No question seems to be there. Okay, so let us go back to our talk again. Well, then we do look at some other special mechanical, other not special, other mechanical properties. For example, we do look at, although it's not expected to take a lot of tensile load, the concrete, we do take, we do look into measurement of tensile strength, and also, because it depends upon how you measure. So measurement, we do look at measurement of tensile strength in case of concrete largely. Now, if you look from fundamentals, this material's particulate system, if you push them from all sides, nothing will happen to it. It can take a lot of what you call, like even soil. Soil, people do triaxial test, right? So you test from all sides, but they have water problems, so they do drained and undrained test and all that, and try to find out the behavior under triaxial loading, because soil below the ground, it will have confinement from all sides, right? So therefore, triaxial behavior, when you have a kind of a hydrostatic pressure from sides and bottoms everywhere it is same, then top you put extra load, how will it behave? That's the foundation. Soil, they look at triaxial. Now, concrete, then triaxial strength will be quite high. If you try to put pressures from all sides, you can't do much. Only after a good lot of load, the voids will come together, and maybe somewhere there will be some sort of crushing and things like that, weakest position and all. But it can withstand significantly higher load than uniaxial. Why? Because in uniaxial loading, Poisson's effect comes into picture, and there's a tendency to expand in the transverse directions, which means that there's a kind of tension force acting there. Now, tension means what? Pulling from each other, which means that particle can be separated. Since the bond between the particulate system is not, it's not chemical bond, it is actually mechanical. More of it is mechanical, most of it, right? It's between aggregate and the binder system. So they can be pulled off very easily. And there are voids in the system, I mean pores in the system. So they act as weakest load, weak points. So flaws. So you pull them, they will separate out very easily, right? So if they separate out very easily, tensile strength will be low. That we understand. That's why it's so high in compressive. Compressive strength is around 8 to 10 times higher than tensile strength. So, but sometimes we need to take care of the tensile properties as well, and therefore we study their tensile properties also. Then elastic modulus. This is very much needed by structural engineers because they would like to find out the deformation under a given load. So elastic modulus is an important property which one would use. EI, is the stiffness of flexural members. EA by L should be, am I right? EL by L is the stiffness, right? So P by A is equals to E into delta L by L. So if I write stiffness P and delta L, yes. So it will be E into what? P by A is the stress into, so P and delta L relationship, P A over L, actually, P over L. That will be the, if delta L is the deformation, P is the force required. So stiffness is related to that, Kx, right? So stiffness is related to that. So again, you see E is coming into picture everywhere. So either axial loading, flexural loading, you need E, elastic modulus. And elastic modulus, uh, again, both of these properties, strength properties or any other strength properties, our understanding is relatively poor, I'll say. Tensile properties, yes, one can possibly understand a little bit better. But E of a composite system, how does it relate to proportion of each component and E of each component? This is still one has to look into. So we don't look into all that, but what we do, we empirically relate E to compressive strength of concrete, the uniaxial compressive strength of concrete. And it's been seen that it's proportional to cube cube compressive strength as we measure to the power n, and nearly close to around 0.5 or so. So that's the kind of properties that we study. The other mechanical properties one would like to know is abrasion resistance, which is basically for pavement and similar sort of thing, where there's a rubbing, and abrasion resistance and then impact sometime. And then fatigue. Fatigue is basically reversal of stresses. So if the stress is reversed, it can withstand, some after some cycle, it fails at much lower load than it would have failed otherwise in monotonic load. So that's fatigue load. Fatigue. So in case of steel, what we see is that if we plot log n versus number of cycles versus failure strength or failure load or proportion, of static as proportion of static strength, this reduces linearly, logarithmically related. So this is called SN curve, strength versus SN curve. But and we see that after certain cycles, 10 to the power 6 or 7 or whatever it is, uh, metals doesn't, it's that S doesn't change, the strength doesn't change. So we call it as endurance limit. So metals still have got a definite endurance limit, 100 MPa approximately, but concrete doesn't have fixed endurance limit. It goes on decreasing. So we talk in terms of number of cycles after which the failure load, we call it as fatigue. And this is also related to compressive strength. But there are other things like we discussed also, I believe, modified Goodman's diagram, because already stressed to a static stress, then how much cyclic stress it can withstand. That is what is shown by modified Goodman's diagram. Then cumulative damage concepts, Miner's rule. This also I think we have discussed in one of those lectures. Fatigue. So these are other properties. Now when it comes to durability then, Durability means that there is a sort of uh, environment specific, right? So concrete doesn't react with everything. And if you keep it in just atmosphere, it will simply doesn't not necessarily react as aggressively as the steel. Steel will get oxidized very fast because it's produced with much higher energy per ton. So it will get oxidized very fast. So it will have formation of at least black rust depending upon the pH around. In an alkaline environment, it forms black rust. In less alkaline environment, it has a tendency to form what is called red rust, which is expansive in nature, which occupies more volume than the original iron, and thereby exert pressure onto the surrounding materials. If it is concrete, if it is embedded in concrete, cause corrosion. So this is aqueous corrosion, but corrosion of metal is of other forms are there, but we are not looking into that. So in concrete, that is important. But when it comes to, reinforced concrete, it is an important issue. Uh, well, so durability, when we look at these issues. So we also look at reinforcement corrosion. Now this corrosion occurs, once I said, at low pH. Now concrete, fortunately, is normal concrete will be at high pH because it is calcium-rich material and there are sodium and potassium in the system. So this one, when in presence of water, sodium, potassium, will form hydroxides. They are alkalis. And calcium hydroxide is also produced. So this calcium hydroxide, sodium hydroxide, potassium hydroxide, blah, 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 these are all alkaline. And they maintain a condition where Fe3O4 would be formed, or Fe2O. FeO, some of them are not stable, but Fe3,4 is quite stable. And this is called black rust. And this density is not, it's quite close. It's not much less than the iron themselves itself. So as a result, it doesn't cause expansion. But if the pH goes down, you can't stop, by the way, from Fe to react. This tendency would always be there. You can control the kinetics. How can you control the kinetics? Put a layer outside. So Fe cannot dissolve in water, in the surrounding water, in an aqueous system, electrolytic system. It's electrochemical. All metal, has a tendency to have electrochemical reaction because they have got extra electron at the outer periphery, outer shell, right? Last orbit. And that is far away from the nucleus and loosely bonded. And that's why metals have got, we assume, spherical particles, spherical atoms, and they all form, they are packed together in a specific way, specific crystalline structure, and the outer electrons are free to move relatively easily. That's why you put a electrical potential, they will move, they're good conductors, etc., etc. So this electron can easily go, and if it goes, then Fe becomes Fe++. Two electrons going, Fe++. Now, if this electron goes to the metal, this Fe++ can also go to the solution. And in an electrochemical reaction, charge transfer is involved. So this charge transfer occurs. And if we can react with something forming some stable, some compound, as long as if it forms Fe3O4, we are not worried about it. But when in a low alkaline situation, in a high chloride situation, that's another one. If the too much of chloride is there, it's got a very high affinity for Fe. So it forms FeCl2, but then that's not stable again. So what happens? It breaks down, forms into HCl, and Fe can go towards, above a threshold level of chloride, Fe goes towards forming FeOH3, FeOOH, H2O. FeOH3, that is what it is. And that's basically voluminous in nature. So this is a corrosion problem. Now corrosions are two types. One is general corrosion, which occurs from internal chloride. And another is pitting corrosion, which occurs if the chloride has come from outside, because locally chloride can be very high. But general corrosion is where chloride is there present in many places. Some places will have higher chloride, maybe some may have less, but it is above threshold most of the places. But metal itself is not uniform. So in some place, some part of the metal, if you have a tendency to get dissolved easily, because it's alloy, and even otherwise, there can be a dent, or just say, even if it is not a dent, There can be chemical difference, physical differences, crystal structure may not be exactly the same, there are defects, several things happen. And therefore, some locations in the metal itself, Fe itself, iron itself, has a tendency to lose electron more easily than others. So those places where it can lose electron easily, Fe++ also goes into solution, that becomes a node. Others are cathode. So where there is anodes are separated by a long distance, or there's a local anode, large cathode, which happens when chloride is coming from outside. There's a local pit formation that we call as pitting corrosion. So this is, the concrete we are talking of, and therefore protect the concrete. It should be as moisture free as much as it is. So electrolysis. So electrolyte should not be there. If there's no water, there'll be no electrolyte, and therefore there's no problem. This is one of the major durability problem all over the world for various reasons. In Western world, it is because they were using, or perhaps now they may not be using as much. Depression of freezing point. Right? If you add sodium chloride to water, it will freeze at a lower temperature than normally it freezes. And elevation of boiling point, it will boil at higher temperature. So depression of freezing point. So if the temperature is low, you add some salt to the snow, it will melt easily, because now the freezing point has become not zero, sub-zero, but it has become higher than what it is. And then you can scoop, removing it has become, so de-icing salts, they are called. And they were mostly sodium chloride salts. And this salt you put on top of concrete bridges, deck, or near concrete structure, this chloride goes inside because it's all moist. Right, so in a way, as if you have a fixed chloride concentration on top of the bridge deck, and inside the chloride will penetrate by diffusion process. Right, diffusion is molecular movement when there's a concentration gradient, fixed diffusion law. So concentration gradient existing, the material move. You are familiar with you. You put sugar into one corner of a big beaker, and you take water from other corner, sip a little bit, or take with a pipette or burette, right? You will not find it sweet immediately. But come after some time, maybe a few days later, you'll find that everything has become nearly same sweet and similarly. Why? Because the sugar molecules will have diffused all across. Brownian motion they would be, and they would go to those places where they are not there. So that's process of diffusion, right? Because of concentration gradient, one can write osmosis is the phenomenon. I don't think I'm going to talk about it here, but it's there. I suppose it's there in the lectures. So chloride can come by diffusion when you add de-icing salts. But in India, we don't do that. So our chloride comes from ingredients largely in continental India, but it may come from the ocean environment, right? Groundwater and ocean environment around the 7,000 kilometer sea coast we have. And if the groundwater in arid area is contaminated with chloride, and if you have used that in construction of structures, it can lead to all kinds of problems. So corrosion is related to that. The other ones which you see is pH of concrete lowering by carbon dioxide of the atmosphere, that we call as carbonation. There are other phenomena like alkali aggregate reaction, so that's all been discussed there. Then other durability problems are seawater attacks, right? That's also has been discussed. So all these are discussed in the one of the modules, actually, several of them, and then how current code is protecting, but what should be the better way, performance-based design, life, estimating service life and all that. Much not, I think little bit has been touched upon this, because this modeling is still the big question. But I think I've given chloride model, conversion model, etc., etc. Those have been given there. Lecture series. That's a module on durable. Then we do look at the shrinkage. Now, the other types of cracks are, I just would like to mention before I go to shrinkage, are intrinsic cracks. Inherently, there is some sort of shrinkage in concrete. That's not much. Chemical shrinkage is not much, because the volume of the solid produced after reaction with water and original volume of cement and water, there's a slight difference, and that we call chemical shrinkage. Very small, but that's very early. But then there is, more importantly, is a drying shrinkage which occurs. So this drying shrinkage occurs if during curing period, if it is dried of RD, right? Then the water that can evaporate from what is called gel pores, which have been discussed in the microstructure of cement hydrates, if the gel pores, if they lose water, there's chance of shrinkage occurring to the concrete system. And if it is restrained, it will stop from shrinking, held it in position, then there'll be tensile crack coming in. Restrained shrinkage can result in, you want to shorten, you are not allowing it. So that can cause cracking. These are called intrinsic cracks. The other intrinsic cracks is thermal cracks coming because of heat of hydration. If the heat of hydration in a large structure, if inside is still warm, outside is cold, there can be differential temperature, and that can lead to thermal, thermal. Again, top wheel, since it's contracted, it has come down to lower temperature, it will try to shrink or contract because temperature has come down, and it would bottom core is still warm, and therefore it's in expanded position. So all this results in differential temperature, can result in a thick section, can result in cracking of the surface concrete, because surface concrete is thermal contraction would be restrained by the warm core. So these cracks are also intrinsic cracks, these are called. They are not really durability related. So we have discussed this shrinkage phenomena. We have discussed this shrinkage phenomena in one of the modules. And then I think also efficient thermal expansion and all that also has been discussed. So these are the books. These are the thing. Then we discussed, I think, fiber reinforced concrete. Fiber reinforced concrete. We have discussed fiber reinforced concrete, right? Right? Okay. Fiber reinforced concrete. Okay. All right. So we also discussed fiber reinforced concrete, and then discussed self-compacting concrete, which is an extension of normal concrete. The only thing is now concrete is versatile, as modern concrete is, because I can have zero moldability. I mean, almost dry as soil, and compact it with road roller. That we call it roller compacted concrete. The other would be I just allow it to flow on its own. That's called self-compacting concrete. But how do I do it? Only thing flowable in the cement concrete system is the powder and the water. Paste, as we call it. So plastic paste, right? Plastic paste. So plastic paste is what we call, and this plastic paste should be fully flowing. So that can be achieved by plasticizing and an appropriate kind of proportioning of the whole thing. And paste content is high in such concrete. So we talked about that. Then we talked about high strength concrete. So high strength concrete. Then I think we have also discussed about all other similar concrete. Roller compacted concrete also, I think we touched upon. Several high strength matrices like MDF, macro defect free MDF, then reactive powder concrete, and these are the ones we discussed in one of the fiber reinforced concrete. Now, as we said, that concrete can, when you are trying to put compression, it expands and fades actually without much deformation. So what we call, it doesn't have this property of long deformation capability, what we call ductility, and you can, or crack occurs. So if you would like to crack a restoration property in certain flexural members, like let's say pavement resists the load by flexure. So crack arrestation. So we actually add fibers to improve those kind of properties. The structural fibers, higher strength fiber, higher modulus fiber. But we do add low modulus fiber to control this property during the plastic state, bleeding properties and things like that. So polypropylene, polyester, there are several fibers Today there are a lot of polymeric fibers, aramide, Kevlar 2949. There are aramide fibers. There are varieties of fibers one can think of. And this has been we did not discuss so much about the fibers, but fiber inputs concrete to discuss. But I think we didn't discuss much about the low modulus fiber there. Okay, so I think let's get some sort of an overview of the course, right? Some sort of overview of the course. So if you still have some question, I'd like to answer, right? I'd like to answer. Okay, I'd like to answer. All right. So any question? Any question? Is Adam eligible? Is I think it's yeah. No, 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 not that, not that, not that. I think. Let me find out. No, who wants to see scholarly article? Nebili CBE, yeah. Yes, that's Adam Nebel. Poland, yes, I think he was born in Poland. That's what I thought. 1939. And during Second World War, he ran away from there, German occupation, Nazis occupation. So he was Adam Nebel. Didn't say Adam M. Nebel. Full name doesn't say. All right. Matthew Nebel. Adam Matthew Nebel. Somebody was asking. He's Adam Matthew Nebel. He's Adam Matthew Nebel, born in Holland. Right? So he was Vice Chancellor of Dundee. Okay. So any question? Any question? Any question? Any question? I've given you an overview of the course. Any questions from anybody? I believe there are not many participants, right? There are not many participants. So maybe they don't have too many questions, and there is a TA who's, there is one person who's meeting them every week. Maybe they're satisfied with the interaction. So, Abhishek, how did you find it out? How did you find this TA-ship?
It's good, sir. I'm enjoying it.
Since there are no questions from anybody,
Uh,
so
it's clarified in the ask a question section. It's there in our Google only.
sorry.
There, people do ask questions in the NPTEL section only. In the query section, they do ask questions, which are
Yeah,
clarified there also.
they do ask. Yes, I know that. Yes, they
Yes.
do. Yes, yes. So yes, something came in the chat box. That is Neville Brooks. Brooks. There's another book, Brooks, as I said, Neville and Brooks. Neville and Brooks. That's a small book, thinner book, but the thicker book, first first person to actually compile any book on this subject was Professor Neville. You get everything under the sun. I'm not sure when it was. I think 50s it must have been published, right? J.J. Brooks. Yes, you are right. J.J. Brooks. Yes. So Cripp is a person of Cripp. I happen to have listened to his lecture in Center for there's a CSMRS lab, Central Soil and Materials Research Lab of Water Commission on Cripp. Just talking of Cripp. They did some work on Cripp. J.J. Brooks. Yes. So yes, Abhishek. So anything? Yes, from Abhishek.
Yeah, yes, sir. Sir, actually, the concrete is a very fascinating thing. Uh, talking about the economical part of concrete, when I started learning about concrete, so with what I found that generally at site, concrete is prepared at a amount of about 5,000 to 6,000 per m cube. So
Mhm.
if I take out the per m cube cost, that is per liter cost of concrete, that is
Yeah.
1 m cube is equal to 1,000 liter. So for 1 m cube, I am paying 5,000 to 6,000. So if I take it out per liter cost, it will come around 5 to 6 rupees.
Yes.
And if you go to market to buy a mineral water, that too costs around 20 rupees per liter. So how cheap it is? Like first I started thinking that why do we use concrete? And then I found this answer that it is because
Yeah.
it is abundantly available, first of all, and next it is so economical that it's even cheaper than water.
Yes.
Water is an ingredient of it, but still it's cheaper. So
Yeah, but
that's the
then
beauty of it.
you have taken only the drinking water.
Yeah,
So
that's the drinking water.
that's why human being uses water most and then concrete.
True, true. Right.
Cement is the next used material after concrete by
Uh,
human being. I mean,
but
after water by
uh,
human being.
right, yeah. But still,
So,
still, it's so economical that
yes, it is. It is because you are using natural material. No,
yes,
see, the modern concrete. I mean, concrete is not really. If you look at it historically, it is not new.
right.
2000 pre Christ, whether
True.
it is in India or it's in Rome, people have used particulate material bonded together. So that's also a kind of concrete. Bonding material has changed. It came as Portland cement after Joseph Aspadine patented it in 19th century. I think it's 1840 or something of that kind. I don't exactly remember. Might be there in one of my lectures, 1825, 1840, whatever it is. So only after that it becomes the ordinary Portland cement. Otherwise, people were trying with lime, calcined lime, and silica. So like that. So they were trying many things, calcining lime, calcining silica separately, adding them up. So why not mix them up together and calcine them? And that gentleman solved that problem. He was actually a mason, but he solved the problem, Joseph Espadine, so that the ordinary Portland cement came by. So concrete has been used by a human being because it's natural material, artificial stone. Good observation by you. That is
Yeah.
as
Yes,
cheaper than mineral water, cheaper than mineral water.
right.
But understanding its science is still quite a bit. You cannot
Yeah.
get the mixed proportion using mathematical equations.
Yes, sir. The
That
more you
thing
go
is
deeper, it fascinates you.
yes, yes, and like it varies from different. I mean, material natural system we are using, so variation is too much from point to point. I mean, like soil is within 100 meters, it will vary. Concrete will vary, let's say, in 100 kilometers because we are picking up something. So, uh, almost natural material we are trying to use. This is one aspect of it. Second aspect of it is we don't have much understanding. Still, we have got to have a lot of understanding of the particulate material system. Chemical engineers looks at it, powder technologists at the powder level, and that's why we have packing density models and things like that are coming. So there are a lot of things to understand, and today course, going finer into the molecular dynamics or nano indentation and all that, they can, model it at that level and measure certain things at that level with nanotechnology. So it's interesting. Yes, it's very, very interesting. Very, very interesting. But not to feel that it is actually very empirical. You can get into the mathematics, which is difficult. Very, very difficult. You want to put in some mathematics into concrete science, not easy thing. Because that's what I'm saying. Modeling is not easy. Relatively difficult. Otherwise, people would have modeled it. Steel is easily well-behaved factory-produced material, very easily put into Hooke's law, things are over. The mechanics is over. Put into electrochemistry, the corrosion part, but there are some problems, of course. But still, you can understand the electrochemistry far better than deterioration of concrete. So, Sandeep Saab, will you tell us when to break? We'll break. I think Muhammad Adam has been asking some questions. I mean, not questions, he was interacting. And not seen anyone else. Oh, nobody's there. Yes, so I think we should, shall we close? Sandeep?
Yes, sir. Yes, sir. Yes, sir.
Okay, तो आप बंद कर दीजिए. मैं अपना वीडियो ऑफ करता हूँ.
ठीक
Thank
है
you
सर.
very much. Thanks,
Thank-
thanks Abhishek.
Thank you, sir. Thank you.